Good morning, people. I'm here to explain a little bit about what we're doing today and show you how to use the chemistry reference tables to answer some of these worksheet questions. So by the time you get to the part where I'm going to show you how to do this in this video, you will have already done your IA and got your definitions. So the slides here give you definitions um, for these solution terms, some of which we have talked about, some of which we have not. Um, Most of them you have seen before, but really the focus of today is these four right here: solubility, soluble, and insoluble. So just like there are factors that affect how fast a reaction happens, there are factors that affect what can be dissolved by what. The nature of the solvent and solute and solvent, that's like the phase of matter, how they interact with things, stuff like that. Bond types, when toward the beginning of the year, when we were looking at ionic versus covalent bonds, and we were looking at the different properties that those two substances have, typically like dissolves like. So ionic things dissolve other ionic, or polar things dissolve other polar things. And it is those mixes of positive and negative charges on molecules that allows them to interact with each other and either dissolve or not dissolve. And of course, temperature. Just like when with reaction rate, generally speaking, if you speed something up and particles are moving faster, we'll have more collisions. So same thing happens when we're dissolving something into water. When we increase the temperature of water, it usually dissolves more. Like when we were doing our rock candy sugar experiment, when the water was cold, it dissolved some sugar, but when we heated it up, oh boy, did it dissolve a lot of sugar. So we're going to be using table F to determine solubility guidelines, and we're going to be using table G to determine how much stuff can dissolve in water. So first, I'm going to use table F. I also attached the chemistry reference tables, the whole reference tables, to this assignment because you need to use both of them. Specifically, you need table E and you need table F. So let's scroll down to this part where we're using this table. Okay, so the first one I give you, it is this compound right here is soluble because sodium and nitrate are both soluble. It's pretty easy to look at this and go, Na, okay, that's sodium, good, got it. But we're not as familiar with these polyatomic ions. Luckily, you have this polyatomic ion table. So look, there's NO3 right there, nitrate. So we have sodium nitrate compound here. Now that we know that our ions are sodium and nitrate, let's look down at table F, which tells us if something will dissolve or not. So on the left side, we have ions that are soluble, and on the right side, we have ions that are not soluble, that are insoluble. These will not dissolve. So where does sodium land? Group 1 ions. Sodium is a group 1 ion. You have lithium and sodium right here, and everything else in that first column of the periodic table is soluble. Are there any exceptions to this rule? No, there are no exceptions to this rule. They're always soluble. You'll also find that you have nitrate down here. Nitrates are also always soluble with no exception. So this compound is soluble because both ions are soluble. So let's look at the second one. All right. We have Ba and SO4. So let's look for where we can find SO4. SO4 is right here at the bottom of the soluble table. Okay, so we know that sulfates are soluble. Oh, and where would I know that SO4 is called a sulfate? Up here, table E, SO4, sulfate. So I find sulfate. Yes, it is soluble, except when it is combined with Ag, silver, calcium, strontium, barium, and lead. Oh, right here, we got sulfate combined with barium. So sulfate is soluble except when combined with barium. So this is going to be insoluble because sulfates are insoluble when combined with Ba. Okay? It's as simple as that. So when you go through, you find the ions that you have in the compound. You compare them to table F to determine if they are soluble or insoluble, and then if there are any exceptions around the rule. Okay? And that's how you answer those. Now, a little more graph reading is with table G. So table G is the actual solubility curves at standard pressure. So this is assuming that we have a mixture of this compound and water, any one of these compounds and water, at a given temperature, but the pressure is going to remain constant. So up the side, we have the solubility in grams of solute per 100 grams of water. So basically, how many grams of solute will dissolve into 100 grams of water at a given temperature? So generally speaking, as the temperature increases, most of these curves are going up. Most of these curves trend upward. Some of these curves do not, like hydrogen chloride, hydrochloric acid, like ammonia. These guys actually, as you get colder, they dissolve less and less gas, SO2, but for the most part, as the temperature goes up, we dissolve more and more of a substance. So how do we read this bad boy? The maximum mass in grams of potassium nitrate needed to saturate 100 milliliters of water at 70 degrees Celsius. So we're going to be at 70 degrees Celsius. So we know that we're going to be reading along this line right here, 70 degrees. And we know that we have potassium nitrate. Where do we see potassium nitrate? Here's this guy, potassium nitrate. So we're looking at this long, very steep curve that goes across the table, all right? And we want to saturate 100 milliliters of water. Well, milliliters of water and grams of water are both 1. It's a direct conversion. So we're just going to find the line on this table. So 7 degrees, and we want to find where this line, the KNO3 line, crosses 70. That's at about 133. Say 133, 134. So what does that mean? That means that at 70 degrees, 100 milliliters or 100 grams of water can dissolve about 134 grams of potassium nitrate. That is the point at which the solution is saturated. It cannot dissolve anymore. It is saturated. So I'm going to link this back to our rock candy experiment, okay? Sugar also takes a very, very steep curve like potassium nitrate, so we're just going to use the same curve right here. Think about this. When we were making the rock candy, we heated the temperature up, way up here. We had the water boiling. So the water became saturated at a really, really high content, high concentration. So for instance, if we have our water at 70 degrees, we have 134 grams of potassium nitrate in there, and then we take that solution and we cool it down, and the temperature drops to 40 degrees. Now, the saturation point is only about 65. So all of this potassium nitrate, this mass of potassium nitrate above the saturation line that's in the liquid, that's what we call supersaturated. And as you cool, that solute will gradually become solid and come out of solution, precipitate out as a solid. So when you give that rock candy a stick or a string, what the sugar does is it goes from being super saturated in that solution to solidifying out, because the saturation point of the sugar or of the solid is decreasing as it gets colder. So it can no longer be dissolved, and this super saturated mass has to become solid again. And that's when it solidifies as rock candy or as salt crystals. All right, guys, I hope this has been helpful. Enjoy working on this, and if you have any questions, please reach out.